I'd like to dedicate this video to all those people out there who think that it takes more skill to make a guitar using hand tools than it does with a CNC machine. In today's video, I'm going to show you all the different files that I have created in order to cut the Delta guitar on my CNC machine. So let's jump on the computer and I'll give you a taste of what goes on behind the scenes. Okay, so I'm sitting here on my iMac desktop computer, and this is where I have created the project for this Delta guitar build. And this project includes all the carving operations that I will need to do on my CNC machine in order to make the fretboard, the neck, and the body. So the program I'm using, this is actually an online program. It's called Easel from Inventables. I've talked about this program before. Inventables created this program to work with their X-Carve CNC machines. And I've been using it since I had the original X-Carve. Now I'm using it with my X-Carve Pro, and I'm using specifically the Easel Pro version of that software. So you access it online, and I'm using Google Chrome as my browser to access it. And what I can do is I can set up all the files, all the carving operations as a single project. And if you look at the bottom of the screen here, you can see all of these, basically they're pages for, there's one for each carving operation, all the way, as I said, the fretboard, the neck, the body, even the control cavity cover at the end. So I typically set these up so that I can do them in the order that I feel is best for successfully making this guitar, so that I won't run into any issues. I like to make the neck first, all the way to completion, so that I can measure the thickness of the heel of the neck, and based on the height of the bridge, where the string comes off the bridge over the body, I can do a quick mathematical calculation to figure out what the depth of the neck pocket will need to be, and I can then set that before I actually get to that part of carving this on my carving the body on my CNC machine. So the very first operation is going to be to make the fretboard, and what you see here is the fretboard blank, and I'll be carving in this first operation the slots for holding the frets. That's where I'll press in the frets. And this was set up in Adobe Illustrator as a 2D file, which was saved out as an SVG and then imported directly into Easel. And then I could set the parameters for carving the slots. And I'm going to be using a 0.024 inch diameter 2-flute spiral upcut bit to cut those slots. And my cut settings are 20 inches per minute feed rate, 9 inch per minute plunge rate, 0.01 inch per depth of pass, and a spindle speed of 20,000 RPM. It's a climb cut strategy for which is basically a counterclockwise movement of the router. And then I'm using a ramped plunge cut. So instead of the bit plunging all the way into the full 0.01 inch depth of cut, it gradually enters the wood at a 20-degree angle until it reaches that depth. That helps to preserve the bit. It's a safer cutting strategy. And when you're using such fine, thin bits as that 0.024 inch, that really helps to save the bit. And I've been using the same bits to cut my fret slots for quite a while now. I've done dozens and dozens of fretboards with the same bit, so it does work really well. But once I've finished cutting the slots, the fretboard will remain clamped to the wasteboard, and I'll swap out my bit for a 16th inch diameter 2-flute spiral upcut bit. And I'm going to use that to cut my fret marker dots as well as the slot for the nut, which will be here at the front of the fretboard. And my cut settings are 40 inches per minute, feed rate, and then the plunge rate is 20 inches per minute. Depth per pass is 0.028 inches. Spindle speed is 18,000 RPM. Again, it's a climb cut with a 20-degree ramp in. And this is actually a fairly conservative setting. I could probably increase the depth of pass. However, when I do the simulation, it's only going to take 2 minutes to cut this. So just to play it safe, I'm just going to keep the cut setting at that 0.028 inches. There's no reason to run it any faster if it's only going to take 2 minutes to cut that file. But once this is done, what I can do next is I can put the material that I'm going to use into the marker dots. So I have a couple of options here. You know, I could use mother of pearl. I could use probably what I'll actually end up using is an 1/8 of an inch diameter walnut dowel, and I'll just insert a portion of it into the hole with some CA glue, and I'll do that with each one of them. I could also mix up some epoxy with walnut sanding dust. There's just a number of different options that I could use to fill that. But I'll do that now while the blank is still clamped to the wasteboard. Because then the next carving operation is going to be the fretboard radius. And as you can see, the screen looks quite a bit different than the others. And that's because this is an imported G-code file. And the way I made this was I started out by creating a full-size, full-scale 3D rendering of the fretboard with the radius. And once that was done, I saved it out as an STL file, which I then brought into Meshcam. And that's what you see here. So this is what the file looks like when it's imported. And then the green is the carving operation, which will form the radius. So to do that, I'm going to be using a 1/4 inch diameter 2-flute spiral upcut bit. It's a ball nose bit, and that's going to give me a really nice finish on this radius. So nice that I can actually go directly to 220 grit sanding, and then if I want to, I can go up in grits to get a really smooth and even a polished level of finish on the surface of the fretboard. So it's pretty far refined at that stage. So that'll happen in this operation here, and it's going to take about 19 minutes to form that radius. Once that's done, I'm going to switch back to an 1/8 inch diameter 2-flute spiral flat-tipped end mill, and that's going to be used to cut the perimeter shape of the fretboard. And this will include tabs that will hold the fretboard into the blank as that bit finishes cutting all the way through the wood. If I didn't have those tabs, once it cut through, the fretboard would come flying out of the blank and would likely break the bit and damage the fretboard itself. So it has to remain in the blank with those tabs. And then once this carving operation is complete, I can remove the blank, cut the tabs, liberate the fretboard from the blank, and set it aside. It's done. So then the next thing I'm going to do is I'm going to install the blank for the neck itself, and that will be clamped to the wasteboard of the CNC machine. And the blank is basically a 4-inch wide, 27-inch long, 1-inch thick maple blank. And in this case, I'm going to be using flamed maple. Now, typically, I usually avoid flamed maple or any kind of figured maple for guitar necks, or at least I used to, because they're unpredictable. They can move in ways that you don't expect and have difficulty controlling. However, as you'll see in a minute here, I have a strategy for dealing with that. But the first carving operation for the neck is going to be to cut the slot for my truss rod. And I'm going to be using a 1/4 inch diameter 2-flute spiral upcut bit to cut that slot. And my settings for this are going to be 150 inches per minute for the feed rate, 40 inch per minute plunge rate, the depth per pass is 1/4 of an inch, and the spindle speed is 16,000 RPM. And as I have been doing so far, it's going to be a climb cut fill method, and then the plunge is that 20-degree ramp. So that will take care of the truss rod slot, and that'll take me about a minute to carve that with the CNC machine. Then once that's done, I'm going to switch bits to an 1/8 inch diameter 2-flute spiral upcut bit, and the plunge, or the cut settings for that are 136 inches per minute for the feed rate, 40 inch per minute plunge rate, 1/8 of an inch depth per pass, and then 18,000 RPM. Again, the climb cut, and then my 20-degree ramp. And what that's going to do is it's going to cut 2 slots on either side, one on either side of the truss rod slot. And those are going to be used so that I can install a carbon fiber reinforcement strips. And those will help to keep the neck stable and to resist the potential for the flamed maple neck to want to warp, bend, or twist. And this should keep the neck pretty straight. So once those slots have been cut, I'm then going to do the front of the headstock, which is what you see here. And this, as you can see, is an imported G-code file. And this operation actually includes 2 different strategies. The first is a rough cut, which will carve out most of the wood. And then it will follow with a finishing pass, which will smooth out the surface. And the bit that I'm going to be using for this is a 1/4 inch diameter 2-flute spiral upcut bit. It's a ball nose bit. And that gives me a really nice surface finish after I have performed that final finishing pass. It's to a point where I can sand it smooth with 220 grit sandpaper and work up from there. But then one of the problems with using a ball nose bit is once it carves all the way through to the other side of the blank, it leaves right at the edge kind of a rounded flare out, which I don't want that. I need to deal with that. So to do that, I'm just going to do a quick perimeter cut with a 1/4 inch diameter 2-flute spiral upcut bit that has a flat tip. And that will cut away that flare out, and it will also help to smooth out the edge of the headstock. So once that's done, I can then proceed with carving the other side of my neck. So what I'll do is I will flip the blank over. And I know some of you will be wondering, how do I register 2-sided carving? And I've talked about that in other videos. So what I'll try to do here is up in the corner, up in the right corner of this video, I'll have a link to where I've discussed how I register my blanks when I flip them over, so I don't have to repeat myself in this video. But then the next carving operation that I'm going to do once I have flipped the blank and clamped it back down is to carve the back of the neck. And as you can see, it stops short of the headstock because the headstock was already cut. So this is going to be another one of those 2 operation passes in one operation. So there'll be a rough cut followed by the finishing cut. And this will be done with that 2-flute spiral 1/4 inch diameter ball nose bit. And once that's done, I'm once again going to have that little flare out at the bottom. So I need to remove that, and I'll do that with a perimeter cut using a 1/4 inch diameter 2-flute spiral upcut bit that has a flat tip. So that will take care of that. And as you can see, I've got these little bumps going all the way around. Those are the tabs. And those tabs will keep the neck attached to the blank so that when I cut through all the way around, the neck isn't going to go flying around the inside of the blank, thereby damaging the bit and potentially destroying my neck. So the next step that comes up in this process of making the neck, And this can get kind of complicated, so bear with me while I try to explain this. But what I want to do is flip the blank over. However, before I clamp it down, I need to remove a portion of the excess blank from around the headstock. And the reason for that is because I'm going to be carving this lion's head logo into the end of the headstock. And since the headstock is going to be, at this point it has already been carved, the headstock will have a thickness of 0.5625 inches. That's how thick I like to make my headstocks. So I have to remove that thicker blank material from around the headstock and then re-register the CNC machine at the home position so that I can precisely carve this exactly where I need it to be into the end of the front of my headstock. I know that doesn't make a lot of sense now, but in a future video where I actually will be carving this on the CNC machine, I'll show you kind of what I'm talking about, so it will make sense. But for now, this is what will result. And what I can do once this is done is I can fill this pocket with what I'll probably use is an epoxy resin with like a darker contrasting wood like walnut or possibly ebony mixed into the epoxy, then drizzled into that pocket and allowed to dry. Then from there I can sand it down so that the inlay is flush with the rest of the surface, and it will look like a nice lion's head logo on the front of the headstock. Before I continue with this video, I wanted to remind you to like, comment, and share this video as a way to support my channel. If you would like to do more, you can either click the thanks button down below and leave a tip in the amount that you choose, or you can visit my YouTube store, which is displayed below the description for this video. Oh, and don't forget to subscribe to my channel so you won't miss any future guitar building videos. So once I've finished carving the pocket for my lion's head logo, the neck is basically finished. So I can remove the blank, cut the tabs, and liberate the neck from the blank. What I'll do at that stage is I will insert the truss rod. Then I'm going to glue in the carbon fiber reinforcement strips. I will then laminate the fretboard to the neck. What I can do at that point is I can measure the thickness of my neck heel. And because I know the height of my fret wire, I can add that height to that thickness. Then what I can do is subtract the string height at the bridge when the bridge is in its lowest position. And that's going to tell me how deep I need to make the pocket in the body for the neck. But before I can get to that point, what I need to do is I need to clamp the body blank to my CNC machine. And what I want to do first is to plane both the front and the back surfaces of the body to make sure they are absolutely flat. So I've created a file to do that. And it doesn't look like much here, but on the right side of the window you can see the simulation of my body blank. And then what I'm going to do is I'm going to do a carving operation which is going to plane that surface using a very large diameter. It's a 1 1/8 inch diameter surfacing bit. And that's going to plane the surface absolutely flat. So the blank will actually start out at 1 3/4 inches thick. And then after I've planed the top and the back of the blank, the thickness of the body is going to be about 1.6 inches thick. So I will plane one side, flip the blank, and then plane the other side. And once that's done, I'm ready to actually start the carving operations for making the body itself. So the first operation, I'm going to clamp the body so that the top is against the wasteboard and the back side is up, because I like to carve the back side of the body first. I do that because, as I said before, I've glued the fretboard to the neck, and I want that glue to dry enough to where I can get a really accurate measurement of the thickness of the heel. So by carving the back side of the body first, I can put off carving the neck pocket till a little bit later, and by then that glue is dried. So I'm going to start with the back, and the first operation is going to involve drilling the holes for mounting the neck into the body. And this is just a simple drilling operation using an 1/8 inch diameter drill bit. The cut settings, I use the automatic settings that Inventables provides. They have a lot of automatic settings for many of the different kinds of bits that we use. Not all of them, and sometimes you have to kind of experiment with your settings depending on the type of material that you're using. But I found that this automatic setting works really well for drilling holes, and that's going to be 140 inch per minute feed rate, 36 inch per minute plunge rate. The depth per pass is 0.125 inches, spindle speed of 12,000 RPM. It's set for a climb, but I'm not sure if that really impacts the drilling operation. I just leave it at that. And it's going to have that ramp of 20 degrees so that the bit doesn't get jammed down into the material. It's slowly introduced to it. But that will produce the 4 holes for mounting the body. Once that's done, I'm going to swap bits for a 1/4 inch diameter 2-flute spiral downcut bit. And that's going to be used to cut the holes for my neck screw ferrules, as well as the outer perimeter of the control cavity recess. And I'm using a downcut bit here because it produces the cleanest edge. There's no fuzzies, there's no chip out, no tear out. It's a nice clean edge. But I will only take it down to 1/4 inch. And then what I'll do is I will swap out that bit for a 1/4 inch diameter 2-flute spiral upcut bit. And I will use that to cut the remainder of the control cavity. And if you look closely, it may be a little bit hard to see, but there are circular recesses cut in here. This top, or this area of wood, is in the top, so the thickness is about 1/4 inch, and that can be a little bit too thick for some of the controls that I'm going to use. I prefer to use the short shaft pots, and then of course the 3-way toggle switches and my 1/4 inch jack have very short threaded shafts. So I have to carve a recess to make this portion of the top about 1/8 inch thick, which is going to allow more threads to extend up through the body that I can thread the nuts for each of the controls onto to secure them into position. But I will do this carve with, like I said, the 1/4 inch 2-flute spiral upcut bit, and the settings for that are a feed rate of 150 inches per minute, the plunge rate of 40 inches per minute, the depth per pass is 1/4 inch, the spindle speed 18,000 RPM, climb cut again, and that 20-degree ramp. So that's going to take 5 minutes to cut that out. Once that's done, I can then switch to a 1/4 inch diameter 2-flute spiral upcut ball nose bit, and I'm going to use that to carve the bevel contours as well as this scooped out area where the neck meets the body. So this is going to be another one of those 2 operations combined into one. First, there's the rough cut, which hogs out the material. And what this does is it leaves a stair-step texture in the wood, which is obviously unsatisfactory. I want it to be smooth, so I'll follow that up with a finishing pass that will smooth out that wood to a degree that I can proceed with finish sanding using 220 grit sandpaper. So once that's done, The back side of the blank is finished. So what I can do is flip the blank over, and again, I'll try to post a link here that shows how I register my two-sided carving. But I'll flip the blank over, clamp it back down, and I'm ready to start with the carving operations on the top side of the body. And the first one that I'm going to do, I hope you can see this, it's pretty small, but I'm going to be drilling holes to mount my individual bridges. And that'll be done with a 16th inch diameter drill bit. And you can see here what those cut settings are. I'm using that automatic drilling cut settings. So that will drill those holes, which will take 3 minutes to do. And then once that's done, I can swap out my drill bit for a 1/4 inch diameter 2-flute spiral upcut bit. And what that's going to do is it's going to cut the perimeter of my neck pocket, my pickup pockets. It will cut out the recess for the bridges to mount into, the holes for the controls, and then at the back of the body I'm going to have a recessed cutaway that will allow for easier access to the tuning knobs on each of the bridges. So I'm using that downcut bit in order to reduce chip out, tear out, and fuzzy edges. It'll produce a nice smooth surface. But for these cuts, I'm only going to go about 1/4 inch deep because I don't need to go any further than that. I prefer to do the remaining depths with an upcut bit to help evacuate the chips more efficiently. So once this carving operation is done, I'll switch to that 1/4 inch diameter 2-flute spiral upcut bit, and I can then proceed with cutting the rest of the depth of my neck pocket, pickup pockets, and that rear recess shelf. Now, with respect to the neck pocket, at this stage, when I'm ready to carve this, I can then take the neck, measure the thickness of the heel, add to it the height of the fret, and then subtract the height of the string off the body where it meets the bridge when the bridge is in its lowest position. And that will give me, that number is the depth that I need to make my neck pocket. So I can set that at this stage to, right here I have 0.888 inches, which is what my simulation in my full 3D mock-up of the guitar was telling me. But if necessary, I can adjust that to more precisely determine that depth based on the actual thickness of the actual neck that I made. That's a lot to say in one sentence. But then I can proceed with cutting this operation, and here is my cut settings for that. And actually, since I'm using a 1/4 inch bit, I'm going to use 150 inches per minute, a 40 inch per minute depth of cut, and then a 0.25 1/4 inch depth per pass. I'll leave the, I'll do the spindle speed at 16,000 RPM because it's a larger bit. I'm going to keep the climb cut strategy here, and I'll leave in that 20-degree ramp plunge. So that means the cutting operation will take about 8 minutes to do this. So it's pretty quick. And then once that's done, I'm ready to proceed with cutting the bevels on the top of the body as well as the perimeter shape. And that's what this operation will involve here. And there's actually, as I've said before, with this type of carving operation, there are going to be two different cuts. There's the rough cut, which hogs out the wood and leaves that stair-step terraced surface, and then the finishing cut, which will smooth that out and leave a surface which I can sand starting with 220 grit and proceed from there. And you can see there those bumps again on the side. That's for the tabs so that the body doesn't go flying around once the bit has cut all the way through the material. And the total time for this cut is about 1 hour and 57 minutes. So this is really the longest carving operation in this whole process. Now I could speed it up if I wanted to, but there's a good chance that the surface quality will suffer ever so slightly. So it's a trade-off. If I'm willing to back down and sand with, you know, a 120 to 150 grit, I could probably speed this up to, you know, maybe as fast as an hour instead of almost 2 hours. But, you know, I prefer to start sanding at 220. I'm in no enormous rush here, so I'm going to go ahead and produce or carve with that finer finishing pass, which will make it easier to sand. Now, since I'm using a ball nose bit to do this carving operation, it's the 1/4 inch 2-flute spiral upcut bit, or downcut round nose bit, it's going to leave that little flare out all the way around the perimeter, which of course I don't want. So to remove that, I'm going to do a quick pass, a cutout pass, using a 1/4 inch diameter 2-flute flat tipped end mill. And that will remove, it'll do two things. It'll smooth out the side. It's also going to remove that little flare out at the bottom that was formed by the ball nose bit. And that takes about 5 minutes to do that cutting operation. So once that's done, the body is now complete. I can remove the blank, cut the tabs, and liberate the body from the blank. And then I can proceed with my finish sanding, apply my finish, and attach the neck. So that should go fairly quickly. But the final cuts in this process, in this project, is the control cavity cover. And that starts out by cutting a pocket in the center of what will be my control cavity cover. And this is obviously the Highland Guitars logo. And this is cut down into the wood. And I use actually 2 bits for this. The first is a 1/16 of an inch bit, which will hog out most of the material, 1/16 of an inch 2-flute spiral upcut bit. That will be followed with a detail cut using a 32nd of an inch 2-flute spiral upcut bit, and that will clean it up and add the details. Once that's done, I can then, well, here I'll show you my cut settings. For the 1/16 of an inch bit, it's on the left side of this panel, 60 inches per minute for a feed rate, 20 inch per minute plunge rate, 0.028 inch depth per pass, 20,000 RPM. Again, it's a climb cut and a 20-degree ramp. The 32nd of an inch bit is a much slower feed rate to protect the bit, 28 inches per minute, 9 inch per minute plunge rate, 0.028 inch depth per pass, which is the same as the 16th, but that works just fine for this. 20,000 RPM, climb cut, and again that 20-degree ramp in. So once that's done, I will switch back to the 1/16 of an inch 2-flute spiral upcut bit, and I will cut the perimeter of the control cavity. Now, there are a number of ways that you can cut out a perimeter shape, and you can clear a pocket, you can cut on the path shape, cut outside the path shape, or cut inside the path shape. What I've found for the control cavity covers, it's best to cut on the shape, because since I'm using a 1/16 inch diameter bit, that means the actual size of the control cavity cover all the way around will be about a 32nd of an inch less than what that path would indicate, because I'm cutting right on it. So what that does is it allows the control cavity cover to fit nicely into that recess, so that there's a slight, tiny 32nd of an inch gap all the way around, and that will account for the potential for expansion and shrinkage of the wood over time, so that the control cavity cover will never get jammed into the recess. There's always the possibility that should something like that happen over time, it could actually split the control cavity cover in two because of the cover getting jammed into that cavity recess. But once that's done, I'm going to remove the cavity cover, the blank, and I'll cut the tabs and liberate it from the blank. Then I'm going to clamp down a piece of walnut. And this piece of walnut will be 1/4 of an inch thick. And what I'm going to do here is I'm going to route a reverse of my logo into that surface. And this whole process, starting with my logo on the control cavity cover itself, the pocket for it, this is the positive, and the negative, was generated using a plugin that is available on the easel program. And it's called Inlay Generator. And what it does is it takes your artwork and it creates the positive and the negative, and it actually calculates the sizes that are necessary so that once this is done, I can cut away this outer excess, take this inner reverse, apply some glue, flip it over, and it will snap perfectly into this positive pocket. And there will also be a gap between the walnut and the maple that I'm using for the control cavity cover that's about 1/16 of an inch thick or wide. That allows me to take it to my bandsaw and cut away the maple, or cut away the walnut, and then I can sand the surface smooth. Now I know a lot of that doesn't make sense, but trust me, in future episodes as I actually do this work, you'll see what I'm doing and how this proceeds and what the result is. But what I end up with is a control cavity cover that has a nice walnut inlaid logo. All right, well, there you have it. Just a brief glimpse into what's involved with preparing the files that I'm going to use to cut the components for the Delta guitar project on my CNC machine. And obviously there's a lot more that's involved in creating 3D models and producing tool paths and G-code and all that. I've talked about that before in previous videos. So you can go back and check those out if you want to know more specifics. You can also post any comments or questions that you have down below, and I'll either try to answer those, or I'll try to provide a link to the videos where I've talked about it in the past. At any rate, I hope you found this video to be useful. If so, give me a thumbs up. And if you want to follow along with this series, I would encourage you to click the subscribe button as well as the bell for notifications so that you'll be aware of when I post up additional videos in this series. And in the next episode, I'm going to prepare the body blank, and I'll also show you the blank that I'm going to use for the fretboard as well as the neck. And then from there, in following episodes, I'm going to actually start carving this guitar on the CNC machine. So be sure to check that out as well. And until the next episode, take care, stay safe, and I'll see you soon.